So what happened, I started here by discussing the general equation for stresses top and bottom for any pre-stressing case. A second. So this component, the first term, which is this big box, you have here two terms inside it, right? This is going to be for the pre-stressing force. And yeah, I understand F top, you're going to have here this P for the axial. This is going to be the pre-stressing force, and this also the pre-stressing force. So these two little components, right, which is this big component, this is for the pre-stressing force. Same thing, the top stress and bottom stress. You see these two components? They are for the pre-stress. The second component, the second big component here is going to be for the applied moment. Whether it's going to be dead load, life load, total load, superimposed, I mean, I don't care. It's just for the applied loads. External applied loads, and this is going to be the internal loads. So I'm going to put it here. I'm going to say this term. I should be using one of these. This is going to be for what? For the pre-stressing. Pre-stress forces. And this component is going to be for the applied load. Again, I don't care. Dead load, life load, superimposed dead load. I mean, it doesn't matter. And this big term here is going to be for the pre-stress force. So let me look quick at the signs and see if I can just use all of these values to be positive values, or do I, whenever I have compressions, need to be negative? I need to study this first. I need to think about it. So I'm going to say, whenever you have any moment applied on a beam, simply supported beam, here's our beam, two supports, you have some given loads, you're going to be creating here some moment. The positive maximum moment is going to be right here in the middle, and most likely you're going to have tension at the bottom, compression on the top. Compressive stresses, usually we use negative sign. For the tension, we use positive sign. So I'd like to inspect these two equations in that sense. It says MC over IG, which means M over S. It can be S top, S bottom, if they are different. So by just looking at this, it shows here negative sign and then positive sign, right? Positive is going to be for the bottom because you have tension, negative is going to be for the top. So it seems to me that now this moment can be just a positive value. Whatever value that you have, let's say that you have moment of 100, you just use 100. Don't think about positive moment, negative moment, no, just use 100. So this sign is going to take care of the tension and compression thing for you. So I'm done with this section. This big section, which is the applied load, now I'm done with it. And whenever I have any beam, whether I put it upside down or I put it in the right orientation, I'm going to end up exactly with the same thing for the applied moment, right? Or applied load. Because if I take the beam here and put the pre-stress in a certain way and then mirror it or put it upside down, this is not going to change the fact that the top stress is going to be negative and the bottom stress is going to be positive. Because this is actually based on the applied load and direction of applied load. It is not based on putting the beam upside down. If you have a given beam and you put it upside down, now whatever that used to be the bottom, now it becomes top. And whatever used now to be top becomes bottom. So the question is, when I put upside down, should I rename it? I'm going to say no. Whatever in the top, I'm going to keep calling it the top. Whatever in the bottom, I'm going to call it to be the bottom. I cannot change the fact that now this point, let's say that you have here a beam, right? Here's a given beam. Can I put it right here? I'm going to say this point here of the beam, I'm going to call it point 1, which is the bottom. This point, which is on the top, I'm going to call it point 2. Now, if you put this beam upside down, are you going to bring point 1 up because you called the bottom? You're going to say no. Usually, you're going to have positive moment at the bottom, which means you're going to have tension at the bottom anyways. So if you put it upside down, the bottom point is going to be always positive and top point is going to be always negative. You cannot change this fact. said, okay, how about this section here? I have here compressive force for the pre-stressing on the concrete. I know it's going to be tension on the steel, but the reaction is going to be compression on the concrete. When I take here P to be positive value divided by AC, this here represents the axial compression effect only. Just a beam under axial load. Whether you put the beam upside down or you put it in the right position, you're going to have usually this negative sign is going to be there. Nothing's going to happen to it. It's going to usually be compression. So just think about this beam here, and then you have compressive forces from each side. You change the orientation, compression is going to be still the same. This is not going to change the fact of the compressive stress or compression direction. Think about it this way. Here's the compression force. Put this upside down. It's going to stay also as compression, which means this section is not going to change, or this term here, the subterm for the axial force, the pre-stressing, is not going to change. Now let me think about the pre-stress itself. What's going to happen to it? Here's the pre-stress, the cable. According to our example or our homework, it used to be like this. Correct? Just give you the correct orientation. But what happened, if I may copy this and paste it here, just for sake of discussion. Just change this for a second. Right? This is the beam in the correct direction or orientation. Now the beam I'm going to put upside down. So what's going to happen to the cable? The cable is going to be doing this. Correct? As if I put the beam this way. Everybody agree with me on this?
Yes.
Yeah.
Let me see the effect of this pre-stressing force when it comes to the top in here. It says here plus, which means I'm going to have here a positive moment. Right? This value here is going to be positive, but this means it's going to be positive moment like tension at the bottom. It's just going to be positive value. When you have here positive value, because usually this P is going to be just numerical value, but right? It means you're going to be doing here tension at the top. So this term means for me in here, tension on the top. So let me write it down. So I'm going to say tension at top of beam. Tension. How about here? I'm going to say tension is going to be at the bottom. Why? Because I changed the direction. Now where's the compression? I'm going to say compression is going to be at the bottom. Let me write this down. This makes sense because look at this. This term here has a negative value, correct? Meaning it's going to give me your compression at the bottom. And this makes sense because look what happened. Here's the axial force. You store the axial force right here. Let's give you like this. Then you move it down here. So I'm going to put here the compression force right here. Now, what is your eccentricity? Your eccentricity is going to be like here, from the center of the beam to the bottom. Meaning your moment is going to be acting in this direction. It's going to be acting this way. And the arrow is going to be coming this way for the moment. Right? You're doing compression like this. So just due to this eccentricity and this applied moment, it makes sense that bottom is going to be compression and top is going to be tension. And this explains the whole equation here, that here due to, again, just for the axial force, it's going to give you compression on the top. For the eccentricity, it's going to creating here some tension because you're bending the beam this way. You're bending it to push it upward. This is going to be positive. And then at the end, you have compression from the applied load. And this makes sense because what we are trying to do here is to eliminate the effect of this compression force on the top, or compression stresses, because of this moment by applying this positive, I'm going to say, stress on the top, by applying the momentum to be in the other direction of against the applied moment. Now let's put it here, put the beam upside down. Once you put the beam upside down, this axial load effect is going to stay the same. This moment effect is going to stay the same. It's going to be compression on the top from the applied moment and tension on the bottom from the applied moment. What's going to change is going to be only these two terms. Because look what happened here. Here's the force. It's going to be right here. Eccentricity. It's going to be the distance from this end of the beam to this center point. How about the moment direction? I'm going to say moment direction is going to be like this. Now, where's the moment direction is going to be? I'm going to say moment is going to be coming this way. Actually, this moment is not good because it's pushing the same direction as the applied load. Meaning, in our example, this sign only is going to be positive, only this sign. And this sign only, which is this one here, is going to be negative. This is going to be the only two signs that you need to replace in your equations. And this makes sense because direction of this moment is going to be the same as the direction of the applied moment from dead load or self-weight or life load. It's giving the same direction. It's going to be causing compression on the top and tension on the bottom. This is all what you need to change in the equation. And you just apply the equation after that. Now, any questions? About this issue? Are we good? Or are we still up in the air?
Actually, Professor, I have a question. So, generally, we keep the signs, right, in the formula when we use it, or it's all numerical?
Yeah, you just put the numeric values and then you keep all of the signs. But only when you put the beam upside down, you're here reversing the effect of the pre-stressing, because usually the pre-stressing is going to be like this. So what I changed, I made the pre-stressing opposite to the normal direction.
Yes, that makes sense.
So the only thing is going to change is going to be the additional moment or the moment due to the eccentricity. But moment due to load is going to be the same. Axial compressive stress in both top and bottom is going to be the same.
Same thing. Okay.
So actually, you're kind of killing the beam here. I mean, here you're resisting the applied load by putting a beam opposite to the applied moment.
Right.
But here, you're not helping. You're pushing the beam down more. So even before you start to load the beam, and don't forget, when you load the beam, you're going to push it down, right? You start to push it down before, which means that you preload it. You put additional load on the top of the load that's supposed to resist. You're not helping. Actually, you're hurting it.
Oh, so that's why the signs changes when we put it upside down. Okay, that makes
Yeah,
sense. Thank you.
no problem.
Professor, we use PI, right? Not PE.
Let me check. Let me see what the problem says. Because it depends on the given information, right? The problem says here, during rigging and shipping of the beam. Now, would the beam cast yesterday or a week ago, or do we know? Do you have any idea when the beam was cast? When the pre-stressing
No.
is taking place? Because if I know, if someone's going to say 6 months ago, I'm going to say, yeah, now it's going to be at PE, not PI anymore, because you have the losses has taken place. Correct? But I don't know. I don't know the age of this beam. I don't know when it was pre-stressed. But let me continue and read this. It says here, during the rigging, the crane operator put the beam upside down. Therefore, the pre-stressing strength was not against, you see, it was not against. It was supposed to be against. Now it is with the same. It is not against the self-weight of the beam. Also, at that time, the pre-stressing has been dropped to PE already. Now you tell me which stress I should use. Is it PI or PE?
PE.
PE, because it says at that time. What time? When they were trying to carry the beam and put in the truck. It was already at level of PE. So why would you check it for PI? If this information is given clearly to you. They said when the guy was trying to carry it, it was, I mean, the stress was already at PE level. So, okay, this is given that at that time, because what you're trying to do here, you're trying to evaluate the stresses in the beam and see if the beam is still useful or not. You're not doing here a design case. You're doing analysis case. It's evaluation for the beam. Are you guys okay? Everything is good?
Yes, sir.
Okay. What is your expectation for the midterm? Is it going to be open notes or closed notes? Closed book?
Expect open notes?
Open notes. Is it okay to use your Excel sheets?
Yes.
I said no before. Why do you want to make it yes now? I just want to be sure that everybody hears me here a few times. So it's going to be open notes, but it doesn't mean that you can use your Excel sheet. All right, let me close this. Are we good about this homework problem or not yet?
Yeah, I get it now.
Okay, any further discussion? Do I need to repeat any of these sections or any of these points? It's okay. If you have any question, don't feel that, I mean, there is no silly question and nothing wrong with asking questions. Maybe someone else wants to ask the same question, but we'll try. So if you have any questions, please go ahead. Before we move.
When it said describe kind of like at the given case, I assumed that it wasn't being loaded, like there wasn't going to be any dead load or live load, superimposed dead load and live load, which led me to, is that correct to think that way? Like we wouldn't need to
But let me
include?
see. I mean, I'm here thinking here loud with you, right? So I'm just taking it. I'm trying here to think in the logical way. It says here the beam, they're ringing it and shipping it. So what does it mean by live load and superimposed dead load? Do you expect it to be there?
Service?
Service load. Is it in service yet?
No.
No, they're just carrying it. So it's gonna be the only self weight, because what is a superimposed dead load? Can someone help me here with definition of superimposed dead load? What is that?
Well, what happens once it's installed?
What is that? What is a superimposed dead load? Like what?
When there is an actual load on the beam.
Like what? What items are we talking about?
Like machinery, like
yeah, tiled, like tiled flooring, maybe
AC
pavement
units,
permanent fixtures.
units. I mean, the guy was just still carrying it at the factory. What AC units, right? What is the definition of the live load? Like what?
people
walking.
Yeah, I mean, now he's shipping, he's taking the beam from the yard, putting the truck. Would there be any people on the top of the beam loading this beam at that time?
No.
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 So it's gonna be only self weight.
You would have opened that.
Yeah. I mean, no one's gonna be jumping on the beam while he's just still putting the truck. I mean, it's not gonna be usable yet.
Okay, with that being said, would we have to then include applied loading to our stress equations?
Which loading? The dead load only, the self weight.
Correct. So we wouldn't need to, you know how in the equation you showed if you just close that tab?
The one was PE that shows total dead load, right?
Right, we wouldn't include MC over I in our equations, right?
Why not? You're gonna have MC over I but it's gonna be for the self weight only.
Oh, I get it. Okay, thank you.
Good. Close this. I don't think I need it anymore. Now, let's see here. What does it mean by design a pre-stress beam? Yeah, just so you guys know, let's say that you solved this this problem here and then use PI instead of PE. It does mean that you're going to be getting 0 in your homework, right? You're going to get some credit, like partial credit. And if you use total load, also I'm going to give you some partial credit, but of course you need to have all the correct information to get full credit for the problem. Now I'd like to see what does mean by design of the pre-stress beam, which is going to be our topic for today. What does it mean by design? Design, usually you're going to have demand, you're going to have capacity. You have demand, which means applied load, the ultimate level. This is the way we do it at Trends Design in concrete structures. Whether it's going to be conventional or pre-stressed, it's going to be the same. And also you need to check serviceability, check deflection, check vibration, check stresses at certain point, and so forth. What we have been doing, we have been just going through this this conceptual principle or idea of the pre-stressing and check the stresses, because we know it's going to be like a major factor. Because at the end, if you want to find out FMN, is going to be just one line, couple of lines. You can finish in half an hour. If you have a problem, you just do it in half an hour, maybe 15 minutes, you'll be done with FMN. But in pre-stressed, the check for serviceability and check for the stresses is going to be a major issue. It needs lots of understanding before you are able to do it. This is why we're going here through it, you know. So if you're doing here trends design, you need to satisfy these requirements. Item number 1 is going to be the bending requirement or flexion requirement. What does it mean by that? It means that the moment capacity needs to be greater than the moment demand. Fmn needs to be more than m sub u. And I said, this is going to be simple. We can do it quick. Also, you need to do shear check, which means Vn is going to be more than or equal to V sub u. And then you do deflection. And then you do cracking check. What does it mean by cracking check? Certain beams, you can design them for certain performance criteria. And this performance criteria, you can say, I don't want this beam to crack. Or I want to limit the crack to this much because I'm close to an area full of chlorides, and this is going to be a big issue for me because chlorides is going to be rusting the cables, rusting the rebars. I don't want to have lots of cracks. I need to control the cracks. Also, I need to check deflection. I want to be sure that I don't have excessive deflection beyond the yield limits or beyond the code limits. What is the code limit? If you guys know, usually total load divided by 240 and live load divided by 360. But during the pre-stress stage itself, I need to check the stresses right at the transfer. And this is going to be the PI and the dead load, right? And also I need to check the stresses at the service load. This one I use M total and then I use F for the stress, which is PE, P sub E. Also, there is something called limited state at failure. I'd like to study the failure condition. I want to see what happened to the stresses at failure. Which is going to be failing first? Is it the steel or the concrete? And just for curiosity, guys, do you recall in conventional concrete design, which failure is preferred? Do you want the concrete to fail first or the steel?
The concrete.
Other
Concrete.
opinions?
Concrete, because you'll be able to see it first.
Okay. What happened if the steel fails first?
Be catastrophic.
Yeah, it's gonna be sudden, right? All of a sudden,
No.
beam is gonna be collapsing. Would you see lots of warning, like lots of deflection?
No.
No,
No.
it's not gonna happen. Just the rebar is gonna snap and it's gonna be coming down. We don't want this to happen. So this is what you call here limited state of failure. In conventional concrete, you can also do it, but not common. In pre-stress, it's gonna be critical. Because generally speaking, pre-stress concrete, you don't have lots of deflection. So the formation is gonna be small anyways. So here it seems that you're gonna have more checks than the conventional concrete, just because of stress concept. The loaded stages, I'm gonna say here's the first loaded stage. And this is what we have been doing, right? But we didn't put it in like one slide, we didn't put it in the list and say this is what you need to check, this is gonna be 1, 2, 3. We didn't do that. We just did it in a simpler way. We start by saying, here's a pre-stress, let me find out the stress top and bottom. This is what I was doing. Compare the top stresses with compression and tension allowed by code, and same thing for the bottom. At both cases. So first is gonna be at the transfer time. At the transfer time, you're gonna have the initial pre-stress, PI, no losses happen yet. And you're gonna have the self-weight, which means dead load. You come here at this case and then you say, what happened if the beam is gonna be getting older in diameter, but was never exposed to its self-weight? It was just sitting on the ground, sitting on the floor. You say, good, it's gonna be less effect. You have the same problem. So the problem is gonna happen once you start to lift it and when it's pre-stressed. This is why when you do the check, you do PI with dead load. If the beam is getting older, this PI is gonna drop down to PE. And you wouldn't have a problem. This is not gonna be an issue because the pre-stress effect has dropped down, and this is not gonna be that critical because this is gonna be more critical when you have PI and dead load because the stress here is gonna be harder than PE. So you should be fine. So only one check at the time of transfer is sufficient before you start to apply the service loads. Now, second stage, when you apply the service load. Now you have the service load. For sure, at that time, the stress level is gonna drop down to PE. You're not gonna be at PI now, right? Because you put the beam to service, it has been a while, the concrete has been cast, pre-stress has been transferred, losses has taken place. Now you're gonna have total load and you're gonna have PE. We have done both of these two steps, but we didn't do the overload. What does it mean by overload? Overload means you design it for certain given load. You say, here's the dead load, here's the life load, I'm good with this design. But all of a sudden, you start to overload it. You put additional load, and you'd like to see the performance of the beam at that time. So we're gonna call this limited state of failure, or it's gonna be when the beam is overloaded. What is the nominal condition? This is when you get to phi mn, the nominal condition, right? Which means it's strength condition. Let's see what happened in a very typical standard pre-stressing beam. Here's the beam section, right? Just like rectangular section. This section is gonna be right in the middle because at each end, usually the pre-stress force is gonna be right here. We're gonna be draping the beam or draping the cable. Let me put it here for you for quick. Cable is gonna be doing this or like this. So this section is gonna be taken in the middle. It is not taken at the end of the beam. So at the beginning, you're gonna be putting the pre-stress force at the bottom here. The stress here is gonna be due to only the pre-stress force. You're gonna have an axial compression plus the moment is gonna be putting compression at the bottom and tension at the top. Conclusion, you're gonna end up with some tension at the top and compression at the bottom. And this is gonna be case B. Look at case B. Case B is gonna be the initial pre-stress stage. Here, you're going to have compression. In the top, you're going to have tension. You know, when you put any load, generally speaking, you're going to be applying tension at the bottom, compression at the top. So this is opposite to what the standard loading is going to do to your beam. So this is good. Actually, you're going to be opposite to what the beam loading is going to be doing to your beam. Now, would you have the self weight with it at the time? I'm going to say yes. So what is C? It's C here, it says self weight and effective pre-stress. Now the pre-stress is going to start to drop. Now you're going to have also the dead load with it if you want to. So what happens? Self weight is going to be doing what? It's going to be doing compression at the top, tension at the bottom. So what happens to the compression? Now because you added tension to it, it's going to drop a little bit. And from the self weight of this beam, you're going to be doing compression at the top. So if you have a little bit of tension, this tension is going to be eliminated. You're going to end up with a little bit of compression. I'm going to say, what happened if I'd like to consider just a standard given beam, and I'd like to see the effect of the loading only. I'm going to say, loading only, you're going to have compression at the top and tension at the bottom, right? So look at this. It is supposed to be like this. Compression top, tension bottom. Now what happened? Now you have compression, compression, which is good. So actually the pre-stressing does something good for you. It is reducing the amount of tension that you have on the bottom and also reducing the compression at the top. Because look at this. Without the pre-stress, you will see here lots of compression on the top. It's going to reduce because the tension that you applied previously. So okay, what is this D? D, you're going to have here total load, total service load. You're going to be adding more compression. And at the bottom, the compression is going to drop down because now you're adding more tension at the bottom from the applied load. I said, great. I mean, this is good. Compression is not going to be the same compression that you'd see if you have only conventional concrete and you're going to have only the total load. So this is good. We reduce the compression on top of the concrete, which means we give it more life. It's not going to break that much, that soon. In case E here, you're going to have the final or the full service load, right? Now we have dead load, superimposed load, live load, the whole thing. So as you see here, we split it into more stages, if you like. And instead of saying the first one is going to be just, you see here, if I go back, I have here two cases, right? This case and that case. PI was dead load, service load was PE. But here I can split it to more. Here I say only pre-stress effect. Pre-stress is self-weight. Pre-stress, self-weight, and what? And the effective. Right? Now the pre-stress has been dropped. And here's going to be the total. And the last one here is going to be at the FEMN, which means at the failure, at the nominal condition. This is going to be the last one. So the first item here for us, pre-stress force transfer, is going to be to this conditions. The second one is going to be this condition, if you like. You can do it this way. And this is going to be the third one. But we split it into more stages, if you like. Yes, okay. Now let's look at the load. What load? The applied load. Let me just imagine here that I'm going to have a beam, simply supported beam. Can be applying some vertical loads. It's going to be two reactions, two supports. And the y-axis is going to be this amount of load. So I'm going to say here's going to be the load. And what is this deflection on the x-axis? Deformation or deflection? It's going to be deflection in this direction. You can say, I understand that the beam is going to be doing this. Correct? It's going to deflect a little bit. So I'm going to be doing this graph here between the vertical load and between the vertical deflection when the beam comes down. And see what happens. This dashed line is for conventional concrete beam. No load, no deformation. Make sense? Right? If you have no load, no deformation. You start to apply some load, you have some deflection. Some load, some deflection. And then at certain point, it's going to be reaching the maximum, which is nominal capacity. After that's going to start to fail. Beam here is failing. So what you're going to see lots of deflection and drop in the load capacity. Now it makes sense. This red dashed line is going to be the conventional concrete beam performance. Now in pre-stressed, first you're going to be putting the pre-stress force. And this is going to be pushing the beam up. So deflection is going to be negative deflection. It's going to be upward, which we call camber. And look at the camber, it's going to be all the way to here. So this is what you start with. When you apply the pre-stress at the beginning, at PI, you're going to be right here at this point. So what happened at this point? We're going to say now I have the camber. So this coordinate or this value from here to there is going to be the amount of camber that your beam is going to see, which is opposite of deflection. Now your beam is like this because the pre-stress, no load yet was applied, right? You're going to be right at this point. But in this graph here, they show another point, which is right at the initial pre-stress. You have lots of camber. Now you put the beam, just let go for a week, a couple of weeks, maybe a couple of months. The pre-stress force is going to drop. It's going to be up to here. Now you're going to have here the effective pre-stress. So the pre-stress force has been dropped. So deflection is going to come down a little bit. So the beam is going to do this. So at the beginning, it was at PI. It's going to drop down here to PE. Now the beam is not loaded yet. This load is not there yet. So I may just move it here, right? So let me repeat this again. At PI, your beam is here. At PE, the pre-stress force has been dropped a little bit, and the beam is going to be coming down like this. Now after that, at this point here, you're going to be starting to load the beam with some uniform load. This uniform load is going to bring the beam flat at the balanced load. You remember the balanced load? At the balanced load, what happened? The effect of the moment coming from the applied load is going to be the same as the moment coming from the pre-stress, from the eccentricity. At that point, the beam is going to be flat, which means that you're going to be right here at this point. And the stress in the beam is going to be just uniform because both moments are going to be canceling each other out. And the stress in the beam is going to be just equal to the pre-stress force divided by the cross-section area of the beam, and the beam is going to be flat. So at the balanced load, the beam is going to be flat, no deflection at all, and the stress in the beam is going to be like this, P over A only. Did we study this before? Did we talk about it, this balanced point? Yes or no? Any question on the balanced point?
Yeah, we went over it, didn't we?
Yeah, I guess. I just want to be sure that you guys are following me. That the balanced load, if you like, or the balanced point, this is going to be the point at which the applied moment due to loads, due to this balanced load, right, is going to be the same as the applied moment from the pre-stressing, which means eccentricity effect. So if this is the case, moment coming from the top is going to be the same as moment coming from the bottom. If you have zero moment, I guess there's no deflection. And this is true because deflection here is going to be equal to zero. And the stress is going to be only due to the axial load divided by the cross-section area. Well, now it makes sense, yes. Now we're going to start to apply a little bit of some loads, right? Our design load is going to be all the way to here. This is why it says here delta life, deflection due to life load. So in here, the balanced load is going to be all the way from this point to this point. This is going to be the balanced load from here to there. Balanced load effect is going to be from here to here. And the amount of balanced load, the balanced load itself, the uniform load that you calculate out is going to be this amount, this ordinate here. And deflection is going to be from here to there, to balance the deflection that, or the camber that the beam was exposed to because of the pre-stressing. Now, once you apply the total load, you're going to see here a little bit of deflection. But deflection is going to be, I mean, it is not the same as the conventional beam deflection. Because look at that, this amount of deflection, actual deflection that the beam is going to be seeing It's going to be from this point to that point. It's going to be this much. We put this arrow here. Now, if you have conventional beam, amount of deflection would have been this much. Look at this. It's going to be this value here. Look at this. It's going to be up to here. This is good. Here in this beam, you see less deflection. Actually, I should have been talking about this. This will be the balance, right? So the balance is going to be here. Now look at the amount of deflection that you're talking about. It's going to be from here to there. It's going to be the difference of deflection, which means total deflection in conventional concrete beam is going to be this much. And total deflection in pre-stressed beam is going to be this much from here to here only. So this beam is great. Deflection is going to be very limited compared to conventional beam. Now, after that, you start to apply some loads, right? Till you reach the overload. And then what's going to happen after this? Now you get to the nominal, which is the capacity point. And then you can study the stress. And look at the stress distribution. This reminds me where, when we were doing here the concrete design review, I can take you back to slide set number 2. And look what happened to the stress distribution. Here's the actual stress distribution in the beam. But we don't like this because it's going to be tough to compute. So what will happen, we use a witness block, this simpler or simplified block for the stress analysis. But this is going to be the actual distribution. So here's the actual distribution of the stresses at the failure point at N, Tn, which means at nominal point. This is to calculate here phi max. Now what happened at the point of transfer? You're going to say, yeah, because if I take you back here a couple of slides, I'm going to say 1, 2, and 3. First, pre-stress, force transfer. At transfer time, you have dead load, you have PI, and then you have total load, and then you have PE, service load and PE. So I said, okay, here's the first point. At the beginning, you just have PI, and then you have this equation that we went through already. Now we know it by heart. You can just look at it and say, this is going to be for PI, including dead load only. It's going to be top and bottom stresses. So we know this. Nothing is new. And this all is going to be all numerical values, right? Then we have also the stress limits that we need to be careful about, right? Top and bottom. We went through this already. This is just repeat the slide from the past, but I'd like here to put it together when it comes to beam design. So at the beginning, here is top and bottom at the time of transfer. And this is going to be the allowable stresses at the time of transfer. FCI. Usually once you see here FCI is going to be the allowed stress in the concrete, which is 70% of FCI prime. So you don't want the concrete stress to go beyond this limit. It's going to be FCI. FTI is going to be also the one in tension. So I said, okay, I have seen this before. And this is going to be the code reference. If you'd like to see where this slide is coming from, you just go here. So we have seen this. Same thing at the PE, at the service load. At the service load, now you're going to have the effective pre-stress, but you're going to have here the total moment. Total moment is going to be due to self-weight, dead load, superimposed dead load, and life load. We have both top and bottom. Also, we have limits that you got to be careful about, right? You have stress limits. And then you have also the reference in the code. Now, what I'd like to do is to see what happened here between the point of transfer and between the service load. I'm going to have a change here from PE to PI. If I'd like to use here this gamma, and this gamma is going to be equal to P over PI, what value do you think this gamma is going to be? If I told you, for example, the loss is going to be 20%, what value would you give to this gamma? How much is this?
80.
80%, right? Which means in this case it's going to be equal to 0.8, right? This is the meaning of this gamma. Now, let's just assume for a second that dead load was just there. And what happened? The stress dropped from PI to PE. Correct? It could happen. You just leave the beam in the yard, you put in the factory, you cast the concrete, you put the pre-tension or the post-tension, and you just leave it there. And all what you have is going to be the only self-weight. Now the stress is going to drop from PI to PE. So I guess I can take this PI, replace it with PE. PI is going to be equals to what? PE divided by gamma. Or I can take PE out. I'm going to say here PE is going to be equal to gamma times PI. Correct? It's going to be the reduced value of it. Now what I'd like to do here is to use the allowable stress fully to the code allowed values. So I'm going to say, what do you mean by that? I say, okay, let me look at this. It says here FCI equal to 0.7, F prime CI. So this FCI is going to be the allowable compressive stress at the time of transfer. And FTI is going to be the allowable tensile stress in the concrete at the time of transfer. What is this FC again? Just FC, not FC prime. This is going to be the allowed compressive stress when you have the service load, and then you're going to have here PE. Same thing. What is FT? The allowed tensile stress in the concrete for the service load condition, which means at that time you're going to have also PE. Now I guess you guys understand what is the meaning of this FTI. FTI is going to be the allowable stresses and tension, because don't forget the top is going to be what? Is this tension or compression? The top at the time of transfer. Expect to be tension or compression? Tension. Because you put the beam like this, you put camber. You're going to be cambering the beam.
Mm-hmm.
If you camber the beam, you expect that you're going to have tension at the top, right? So you'd like to use this beam efficiently. You know, when you do a beam design, let's say in conventional concrete, just to give you here an example of how we do it, you have two ways of doing this. It is either that you can assume you can throw there some reinforcing, and then you figure out phi man, you compare it with M sub U. This is one way. Another way, you set the capacity equal to the demand, and then you figure how much AS is needed. Does this make sense or no? Yes, no, not clear?
Can you say that again?
Okay, let me repeat this. I'm gonna start something just here on the cover. I say, okay. Usually, what we do, we say, assume AS. Is this what you guys do when you have concrete?
Yeah.
Because the section is given. So based on this, you find out phi mn, correct?
Yes.
And then compare with what? M sub U. Am I correct? This is what you do here in conventional concrete design, or no?
Yeah.
Okay, but there's another way of doing it. What you can do here is say phi man equals phi, I'm gonna just call it like F, right? Times AS times Fy times D minus A over 2. Anyone recognize this equation?
Yeah.
Yeah.
Yes.
Yes, equation. So again, in concrete design, you can have here two options. One option to assume AS, and then you solve for phi man compared to M sub U, because M sub U you have it, right? This gives you the applied load. The second method of doing this, you say, you know what? Let me put here phi man equals to M sub U, because I'd like to use this beam efficiently. I don't want to throw lots of rebars. Because what happened, I can put, let's say, lots of rebars, get higher MN, and then start to reduce AS little by little till I'm going to be covering just M sub U. But someone can say phi man equals to M sub U, and I have the M sub U value, right? I have this numerical value equals FAS Fy D minus A over 2. So in this case, you don't have AS. AS is gonna be your unknown. So I'm gonna say this AS, I don't have it, you know? AS, I don't have this AS. So in this equation, the second way of solving this problem is to set phi man is gonna be equal to M sub U. And once you do this, you can solve for this AS out of this equation. And after you solve for AS as in square inches, you see here how many rebars you'd like to go with, right? And then after that, you put, I'm gonna be using, let's say, 3 number 7 or 4 number 7. It's gonna be good. Am I clear now about the different approach in design? One approach is just to estimate, to throw some rebar there. You say, I'm gonna be using here 6 number 7 at the first equation, right? At the first method. And just solve for phi man. And then you check, you compare it with M sub U. If you cover it, this is great. If you cover by a lot, you're gonna say 6 number 7 is not. I mean, this is just too many rebars. I'm gonna make him 5. I'm gonna make him 4. I'm gonna make him 3. As long as you can cover M sub U, you're good. Then you keep reducing the amount of rebars because you don't want to put too many rebars, right? In the second method, from the beginning, you're gonna say phi man is gonna be equal to M sub U, which I have this value because M sub U, you can solve for it at the beginning, right? It's gonna be like the given loads. And then you go here to this equation and then you solve for AS as in square inches. Once you have it, you pick the rebar size and then you come up with a number of rebars. Now your design is gonna be right there. It's gonna be very tight. It's gonna be perfect, very efficient. Your phi man is gonna be very close from M sub U. So you don't really need to go through iterations. But in the first method here, you throw rebars and then you go in the first iteration. If you don't like it, you add or reduce the amount of rebar till you approach M sub U. Are we good about this or no? Not yet.
Yes.
Okay, good. All right.
Yeah.
So we'd like to do something very similar to this. In the previous problem, and here's the way it works, we said, okay, let's balance this certain amount of load. If you recall, the way that we came up with number of 7 strands, that I said, let's balance 90% of the dead load. That was an approach, just to think about balancing the load. Think about deflection. But here I'm gonna be saying, no, let's use the stress efficiently. Because after you came up with the number of strands, you start to check stresses top and bottom, right? Top and bottom. At the initial, top and bottom at the service. And then you say at the end, yeah, it is lower than the limit. This is good. But in this slide set here, what we are trying to do is to set the stresses to the allowable stresses by code. And then see exactly the section properties needed. Meaning, when you look at this equation here, in order for you to solve this equation, you need to have AC, correct? To start with. Which means I need to give it the section. I need to estimate the section. I'm gonna say, let's say 16 by 24 or 12 by 24. I need to come up with the section and propose a section for you that you don't know at the beginning if this section is gonna be good or not. And then also I need to come up with C sub T based on the section properties. Also, I need to come up with R squared based on section properties. S top and S bottom based on section properties. Meaning I need to give it the section first. Very similar to what we have done here. I need to give it the reinforcing first. And then check phi man versus M sub U. But in the second method, I start to set demand is gonna be equal to capacity. And based on this, I figure out AS. Similar concept, I'm gonna come here and say, you know what? I don't have this S sub T. I don't have this CT. I don't have R squared. I don't have AC. I need to come up with a method with some equation to give me the needed cross-section properties. I'm gonna say based on what? I'm gonna say based on the applied load. Based on the expected eccentricity. Based on the allowable stressors. Top and bottom. I'm gonna say at the pre-stress time, at the service time. This is the reason that we're going to start here to see the equation that we're going to be setting the stresses top and bottom to the limits by code. So we're going to be setting the stress, which is the stress here on the top. We're going to set it to be the same as the maximum allowable stress. What is this FTI? If you'd like to see FTI at the time of transfer, it's gonna be here. Look at this. FTI is gonna be here. This is gonna be FTI. It's gonna be 3 square root of F prime C at any other location, because now we are gonna be checking the middle of the span. But here, this is gonna be only at the end. This is gonna be at the middle of the span. So 3 square root of F prime C, I is gonna be the allowable tension. Maximum allowed tension here, I'm gonna put it in my equation here. I'm gonna say, you know what? I don't have the section properties now, so I'm gonna set the stresses here. I'm gonna set it to the limit, to the worst case. So I need to reduce the beam size to the extent that's gonna bring the stresses right to the limit. So I can take this equation. I'm gonna set this equals to FTI, which is the mean, the maximum allowable tensile. Rearrange the equation, bring this here, bring this there on the other side. And then I'd like here to find out the difference between the stress at the initial time and at the transfer time. Excuse me, at the initial time and at the service time. I means at the initial time, time of transfer, and E is gonna be the effective. So let me go back here a few slides just to show you what I'm talking about. At the initial time, the stress allowed here is gonna be 3 square root of F prime CI. So I can solve for this numerically. I have the amount allowable stress that I'm gonna have here right at the time of transfer. You have the same thing if you like. If you have here this class U, which means tension, you need to keep the stresses within 7.5. It's gonna be uncracked. It's gonna be transition, it's gonna be between these two values. It's gonna be cracked. It's gonna be okay to be more than 12 square root of F prime C, but you need to provide reinforcing. So let's say I'd like to design here for uncracked. So the initial time is gonna be 3.5, 3 square root of F prime CI. And at the service is gonna be how much now? Is gonna be lower than 7.5, which means it's gonna be equal to 7.5 square root of F prime C. So I have here two limits for the tension stress. Difference between the two stresses, I can solve for it, and this difference is gonna be called the change in the stress between PI and PE with the dead load only. You see what happened? I have only dead load in the beam. And I'm looking here for the beam section properties. That if I put it there at the time of transfer, I'm gonna be right there at the limit. And the same beam, if I put it there at the service time, I'm gonna be right there at the limit. So I'm wondering what beam section is gonna give me all of that and what information you need to look at.
Professor, I have a quick question. Why is the symbol right in front of PE over A positive?
Hello, excuse me, what did you say? I'm sorry, I didn't hear you.
It's okay. I have a quick question for this. The symbol right in front of PE over A, is it positive because we're looking at the difference? PE.
Oh, because this is gonna be the difference.
A different. Okay, I get it.
Yeah, this is gonna be just the difference, because you see this is gonna be the difference between the two. Look at this equation here. When you go back, usually you're gonna have this negative sign, right? So it's gonna be PI minus the one for the E. So it's gonna be negative. This gonna stay negative, and it's gonna be positive. It's gonna be negative, stay negative, and it's gonna be positive, right? Look what happened in the equation. So I'm gonna be taking the stresses here at the time of transfer, subtracting the stresses at the time of E, which means the service.
Okay, yeah, just checking. Thank you.
All right. Now I know this fact here that PE is gonna be equal to gamma PI. So if I take the difference here between the stresses, right, I'm gonna call it here delta F on the top. I can summarize this equation like this. Because in here, what terms do I have? I have M dead load divided by ST, M dead load divided by ST. This is going to cancel out. So the change in the stress, it is not going to be actually due to any applied loads. At the end, this is going to be equals to PE minus PI. Look at this too. And I know that P is going to be equal to gamma PI. So I can put the whole thing in terms of PI if I know the amount of losses. So my equation can be just changing for the change in the stress to be like this. Just by subtracting the stress. And the initial, right? You subtract, you say minus the stress at the service. So the change in the losses, this can be the change in the stresses due to the stress losses in the pre-stress cables can be given by these two equations. See, great. So what's going to happen after this? What's going to be our goal? Let me jump to the conclusion. I don't want to go through all of this. This is going to take lots of time, and you guys should be able to figure it out. It's just taking the equations and add them together and subtract to find out the stress top and bottom. At the end of this exercise, you're going to see here the top section modulus, S top and S bottom, needs to be greater than this given equation. So how were they able to reach this conclusion? By setting the stress limits to the maximum allowed stresses. Very similar to this concept. Instead of throwing the amount of reinforcement that you'd like to put there as rebars and then figure out phi man compared to his M sub U, instead of doing this, you set Mn or phi man is going to be equal to M sub U and then solve for AS. And here we did very similar thing to it. We set the stresses here to the maximum stress limit allowed by code. And then based on this, we solve for S top and S bottom. And S top means what? Section property. One of the section properties, right? So what we need to do after we have S top and S bottom, minimum values needed because it says S top is going to be more than or equal. S bottom is going to be more than or equal, right? We're going to be looking through tables, similar to the steel tables, but we're going to call it precast tables, right? And then look for that section, this concrete section, is going to be satisfying these two values. It's going to be that simple. Now let's look here. This S top is going to be based on what? It's going to be based on gamma, amount of dead load, amount of superimposed dead load, amount of life load. It's going to be also based on the maximum allowable tension at the time of transfer, subtracting the allowable compression in the concrete at the surface level. So in this equation here, it relates the needed section modulus, this is going to be required or needed, based on dead load, superimposed dead load, life load, amount of losses, allowable tension at the transfer time, because we are expecting tension at the transfer time on the top of the beam, and allowable compression, because we expect some compression on the top of the beam at the surface level. Now, if I am solving here a homework problem, or if I'm taking an exam, do I need to solve for this and see where it's coming from? I'm going to say no. It's just for understanding how the equation was compiled all together and how we're able to reach this conclusion. Same thing here for the bottom stresses. I'm going to say the section modulus at the bottom, this is going to be for the same section. So your concrete section needs to have a minimum of section modulus for the top and section modulus for the bottom to be greater than this given equation, right? This is going to be equal to what? Same thing, gamma, which means the amount of losses, multiplied by M due to dead load, superimposed dead load, and life load. So it accounts for all the loading, very similar to this. But what do you expect at the bottom? At the bottom, I'm expecting some tension at the surface level. So it's going to be the maximum allowed tension at the surface level by code. At the beginning, I'm expecting compression at the bottom. You remember when you have the pre-stressed beam, you apply compression at the bottom, the beam is going to get cambered, which means I'm expecting compression at the bottom at the time of transfer. This is why it says FCI. What is FCI? Allowable compression in the concrete at the time of transfer, at the initial. And here's the pre-stress losses, the gamma applies for the pre-stress losses. So again, FC and FTI, FT and FCI is going to be the code limits for the stresses in tension and compression. If it says here I is going to be at the time of transfer, initial. If it doesn't have I, it means at the service level. Where'd you get these values from? FTI, FC, and FT, and FCI. I'm going to take you back. I'm going to say we have them all here. It's going to be this slide. Here's FCI. Here's FTI. Or it's going to be this one, actually. Someone's going to say, how about FC and FT? The allowable stresses at service. You can say they're right here. Here's FC, 0.45 F prime C. How about FT? 7.5 square root of F prime C. So great. I mean, this is good, because actually all what I need to do, just take this equation and this equation. If I know the concrete properties, now I have FTI and FC, FT and FCI. And if I assume here the loss is going to be, let's say, roughly 20% or 15%, it means this denominator is given to me, and now I have it. I can solve for this. Now you give me the beam span, meaning and dead load, superimposed dead load on live load. I should be able to figure all of this. So based on the beam information, such as the span, dead load, superimposed dead load, live load, concrete properties, and the amount of expected pre-stress, I can figure out the section properties needed. I can figure out what is top that I need, what is bottom that I need for this beam. So great. If I do this, and later on I'd like to check the stresses top and bottom, the instantaneous or initial, and then the effective, it shouldn't be a problem, because I know I'm going to be satisfying it. Because the values that I picked up, these values, ST and S bottom, are based on setting the stresses top and bottom to the code limits in both the initial and at the service level. Okay. Gonna skip this part. We'll come back to it. I guess this equation, guys, you have seen it, right? Let me go through this example now. Here's one example. The span is given as 65 feet. I have the dead load, expected self weight of the beam. Just expected, proposed, something that I can start with. Superimposed dead load expected to be 100 PLF, pound per linear foot. Live load is given also, 1100. Concrete strength is given. The strands are also given. It's going to be 270,000 PSI, the 270K strands. Concrete strength is going to be 5,000. Expected F prime CI at the time of transfer is going to be 3750. The gamma value is going to be 18%, which is the losses, right? Is this gamma value, or gamma is going to be 92?
Yeah, 82.
82. 82 or 92? 82. You're right. Thank you. All right. Now I have a couple of equations here that I can use. So let me use these two equations and see what happens. Let me find first the allowable stresses. You see this allowable stresses? FTI, FC, FT, and FCI. Let me solve for this first. Based on the two slides, the code limits I can solve for, as you see here, it's going to be FCI, 60%. It says negative here just to tell you there's going to be compression, but we don't really need to do this negative sign, but just to make it simple for people. Certain people prefers it that you like to see the negative sign for the allowable compression. It doesn't matter. I mean, if you're solving it, it's okay. Just to have positive value called compression, then you don't put the negative sign for it. It's going to be okay, as long as you put compression. For the tension, It's gonna be 3 and 6 at the end. How about for the compression at the time of service? You can say here, I'm gonna have negative 45%, which is 45% of A prime C. And for the tension, 7.5 square root of A prime C. It seems that we don't want it to crack. This is gonna be our limit. So for gamma, gamma is gonna be 82%. Okay, good. What should I do next? You can say next, find out moment due to dead load, moment due to superimposed dead loads, moment due to life load. The span is 65 feet, simply supported. Dead load, we assume this is going to be 85 or 0.85 Kip linear foot. Superimposed dead load, we say it's going to be 100 P left, meaning 0.1 K left. It's going to be 1.1. Find out the moment, Kip foot, and then find in Kip inch. How do you do the transfer here to conversion? You multiply here by 12. Kip foot to Kip inch. Why would you like to see it in Kip inch? Because if you look here at this equation, this FC and FTI is going to be in K psi or P psi. And all of this moment, it needs to be in pound inch or Kip inch. It needs to be in inch, as long as this is going to include here an inch in the value. Now I have the moments. Now I can use my equation here. The required is top and the required is bottom. I have this simple equation. Going to be using all the values just calculated out for. It says here y minus gamma, which is 18%. And then it has here the dead load, superimposed dead load, and the life load. And then you have all of these values. I said, great. What should I do next? I said, this is going to be here the minimum required is top and the minimum required is bottom. Now I need to go through some tables and find out S top and S bottom for all of these sections and pick one of them, the one I'd like to use. As long as the section that you pick is going to have section modulus more than this value in the top and more than this value in the bottom, you should be fine. Your beam should be fine stress-wise. It should satisfy all the requirements of checking the stresses top and bottom, initial and service level. We picked a T, like a single T. It's called 10ST48. And here are the properties of this section. And you see, this is going to be the needed, the required, and this is going to be the provided. You see the provided here, right? It's going to be a lot compared to this. You need 36, we give you here 48. You need 35, we give you here 13,000. So you have enough. How does it look like? I'm going to go here. It's going to be single T. They call this 10ST. 10 stands for the width, 10 feet. ST is going to be single T, and the depth is going to be 48 inches. And in the same table, you have all of these properties. So I'm not going to solve for it. It's going to be all given. The self weight, I assume it's going to be 850, but the actual self weight is going to be 815. This is good. So my estimate was not bad. It was a little bit higher, but it was okay. Now here are all the properties of this section that you can just look it up. You read it off this table. You see here the cross-section area, moment of inertia, the R value, C bottom, C top, and then you look here at S top, S bottom, eccentricity, eccentricity. What is this eccentricity for? You say this is going to be eccentricity for the cable. Actually, you're not going to be really assuming it because it's going to be given to you. They said, if you like to do a single T like this, and you come here to our factory, this give you the recommended value that we'd like to use. This give you like our standard of industry.
Professor,
Yes,
what is V over S?
we'll come to it.
Okay.
You come to it. So all of these values, right, is going to be like recommended for you. Why do we recommend it for you? Because it's going to be our standard industry. We have certain forms and certain equipment ready and certain setup. So we'd like you to use these values if you can. This is why you're not going to come up with your specialty and build it from scratch. No, you'd like to go there to a precaster and just buy this item. So if you like to do this, you're going to be just taking these values from his let's say catalog, and the catalog is going to be this PCI manual, and this PCI manual has all the standard size. I said, great. Concrete strength is going to be 5,000. FPU is going to be 270 KSI. So good. Now let's figure out here the amount of pre-stressing that you'd like to use. So I'm going to say, well, at the time of transfer, I'm going to have here 189. So this is not really J. This is FPI. It's going to be 70% of the 270. I guess we went through this before, right? We said usually, if you guys recall, we're going to have 270. You apply pre-stress of 189, and at the end you get 150 KSI. Am I correct? That with the values. I said if you don't have any values, use the 3 values. 270 is going to be the ultimate, 189 at the time of transfer, and 150 assuming that you have 20% losses. In this specific example, it says loss is going to be only 18%, not 20%. So the effective is going to be 82% of the jacking. Sometimes they call this FPI, since J stands here for jacking, J or I is going to be initial. So it's okay to use J. I mean, it's not wrong. I personally prefer the I. But in this solved example, because it's going to be, this solved example here is taken from textbook, I'd like to keep it the same as is. So it says PJ is going to be at the time of jacking the stress. So it takes here 82% of the 189. You're going to be at 155 instead of 150 KSI. Right? I guess I have this equation here, right? What is this equation about? Now we're going to be doing the actual stress in the beam. Do you really need the actual stress at the beam? Yeah, I'd like to see what stresses that we have there based on this given information. And then based on this, I'm going to be figuring out the amount of pre-stress. Because if you look here at this equation, if you look at this equation here, this dead load, you have it. Stop, now you have it because you picked the section. See what happened? We picked the section. We picked the side of the section, which means now we have the cross-section area, we have CT, C bottom, we have S top, S bottom, we have all of this nice information, R squared and the whole thing. But we don't have the amount of pre-stress force that we need to put in there. So when I look at this equation here, I'm going to say I have M dead load, I have S top, I have EC, I have C top, I have R squared, I have AC. I have this to be the allowed tensile stress in the beam based on the code. And I guess with that, I should be able to solve for PI because I don't have the stress, the applied stress there. So I said, okay, here's the dead load. Now this is going to be based on 815. This is not here based on 850 because now I have the actual size. And based on this, I can find out the amount of pre-stress force that I'm going to put there to set the stress in tension to the limit. So this amount of pre-stress force based on this equation is going to set the stress to 183.7 psi. Meaning, if you reduce the stress, let's say you make it 450, what's going to happen to the stress here? It's going to reduce a little bit. So is this compression here, force that you put in there, is going to be the maximum or the minimum? Can I increase the pre-stress a little bit or I cannot? Can I go to 470 or should I go to 450? Which one would you go to?
$450.
Why not 470? I'm happy with your answer, but you need to justify. Why don't you go with the other side, with the other bound?
Because that would exceed the limit of stress allowed.
It's going to be increasing the stress. It's going to give you higher stress than the allowed. So it's going to be like the upper band. So if I say here one cable or one strand, it has a cross-section area of 0.153. It's going to be stressed to 155. Don't forget about the 150, right? The 150 is the standard. But in this specific problem, I have it as 155. How many rebars would I try or would I use? It says here 16. Can I go to 17? I'm gonna say no, because you go to 17, you're gonna be putting here more stress force, and this is stress, right, limit. You're gonna be going beyond the stress limit. You're gonna be going, let's say 185. So the beam is gonna be failing. This is not good. You need to reduce it. You cannot really use 17. Use 16 or lower. So here we say, let's try 12. Okay, so this is okay. To go to a lower number than 16 is gonna be okay. Nothing is wrong with this. Now we try to figure out here the total cross-section area of the strands. I'm gonna be taking here 12 times 0.153 for just one strand. PI, you're gonna be taking this FPI. How much was FPI? Anyone remembers? You guys remember this? Yes?
189 KSI.
180.
Yes. Good. How about this number in this specific example?
155.
Yeah, exactly. So now I have the stress and forces. And if you follow the stress and forces here, the stress is top and bottom. Should be fine on your beam at the time of transfer and at the service level. Here is PE at the end is going to be 248. This is going to be the number that we use, 248. Not like just check the stresses, just for the sake of explaining what's going on. But I know for sure this is going to be okay. Why? Because I went to a lower number than needed, like 16.13 for the pre-stressing, to keep the stresses at the worst case, at the maximum, at the code limits. So in this case, what do you do? If you go to higher number, you're going to be cracking the beam, and the beam is going to be in bad shape. You're going to break it. If you go to lower number, you know for sure you're going to be okay. But let's check the stresses just in case. So we wanted to check the stresses here at the service level. We said now we have PE, right? The 284. We have all the section properties for this single T. We have the total load or total moment is going to be this value plus this value plus that value. We have S top. Now we can check the stresses top and bottom at the service level. We said great. You have here negative 617. It says here is going to be lower than 3,000. Someone's going to say, shouldn't be this like negative 3,000? I'm going to say yes. I mean, you understand that this FC is going to be compression. So I'm going to say this is going to be compression. So when you say here, C means compression. T here means tension. It does mean top, right? This means tension. Sure, good. Look at this number here. 332 versus 530. It makes sense. Because if you put 16, you're going to be very close to this number. We put 12, where it's going to be slightly lower. So it seems to me that this tension was really controlling our design. It was not the compression. For the compression, we have good range from 617 to 3,000. We still have room. So some of this limit is going to be really controlling the number of tendons that you need to put in there. It doesn't mean if I'm going to put here 16.13 cables, which means if I have this tension force, if I'm going to put this tension force here like this PI, like the number I have here, the 466.5, if I put it there in my equations, it doesn't mean tension compression at the initial pre-stress is going to be right there at the limit. One of them is going to be at the limit. Only one of them. Actually, I have here 4 limits. I have tension compression at the initial. I have also tension compression at the service, at the effective. Only one of these 4 levels is going to be controlling this number here, the 16.13. It seems to me it's going to be this tension, because this is the one that's going to be close to it. It could be this, or it could be the other tension. But it is not the compression at the service. It is not, because look at the gap. You have still a long way to bring to this compression stresses. But here, it's kind of close, like 60%. Let's look here for the stresses at support, because we have also stress at support, stress in the middle. So we're going to be checking the stresses here at the support. And of course, we have a little bit of different limits, and we have all the limits in the first two slides. We check the stresses at the time of transfer initial, and we're still okay. I mean, nothing is wrong with this. Here's allowed. Here's allowed. Look at this. 367, 181. 2250, 2162. Now I want you here to tell me which one is controlling. Is it this stress level? I'm going to call this to be number 1. Compression at time of transfer at the effective, which means at the service level. Or tension at the service level. Or tension at the time of transfer. Or compression at the time of transfer. Which one is controlling our choice of 16.13?
Compression at time of transfer.
Yeah, how's that? How do you explain this to us?
I'm guessing because they're really close in numbers.
Yeah, which number? Let me put this arrow here.
Um,
This number and this number here, right?
yes.
Just take this, the numerical value, 2162 divided by 2250. How much that value is? Can you help?
I got a 0.96.
0.96. Okay. How about this number here? 181 divided by 367. Are you going to say maybe 50%?
Yes.
Plus or minus? Okay.
Yes.
So you still have long way in tension, right? At what? At the time of transfer. Let me go back here. How about here? How much is this when you compare 617 to 3000?
0.21.
How about here? 6%?
0.63. Yeah, 0.6.
Okay, 0.63. So the closest one to bring the stresses right at the limit is going to be this guy here. It's going to be 0.96, which means the controlling factor, right, that we have is going to be the compression at the time of transfer. This is what's controlling your design. Make sense? Yeah.
Question,
Yes.
question?
What?
A quick question.
Yeah.
For E, sub E, does that mean effective eccentricity?
This C sub E?
E sub E.
Not really, because eccentricity is the same. It's going to be the same as eccentricity. It could be just a typo. It's just a typo. It's just EC and EC for the concrete.
Okay, and real quick, why do we include PE for point for A, and right here B check stresses as support? It's I instead of E, P, I.
This one here, I, because it's going to be at the time of transfer. You see
So
this
I
here?
thought I was initial.
Yes, I is initial. This is true. I is initial, the 374.47. So this analysis here is going to be based on the 347.
And that's because we're looking at the initial and then seeing the difference at transfer?
This stress check here is going to be at the time of transfer. See this one as the time of transfer?
Mm-hmm.
And this here check at the midspan when? This is going to be at the service level at PE. So here is going to be based on PE. All of this value is going to be based on PE. And the time of PE at the service level, you're going to be using FC and FT. At the initial time, at the initial transfer or time of jacking, this is going to be FTI and FCI. And this is going to be the value that you use in your analysis, which is PI and PI.
Okay, that's good to know. Thank you.
No problem. Also at service load, if you like, right? This is going to be at the support. This is a check where? At the midspan, check at support, and check here at the support at service level. Just last check that you can do. We're done here with our slide set. Again, this limits from the first 2 slides, if you like. Now you try here the stresses, right? This can be here effective at service. This should be in C and C. I mean, there's not like E sub E, right? It's just a typo. See, this can be EC. And with that, you get here 148 and you get 1773. Don't forget that here you don't have the moment component because the support moments can be equal to 0. And you see that you have no problem at all at this location. You see that. And you still have long way, right, to break the concrete. So what is really important, just to conclude for today's lecture, what's going to happen here? For me, just go back to this guy here. These 2 equations. So this slide 17 is going to be the most critical one that we really need. You have given a beam. You have the dead load. You have the superimposed dead load. You have the life load. You have the span. You can figure out M dead load, superimposed dead load, and life load moment. You have all of that. You have the concrete properties. You have the expected losses. You can go with 20% or 18%, whatever value that you have. Most likely in our beams, we use here 20%. So this gamma here is going to be equal to 0.8, if you like. So 1 minus gamma is going to be, let's say, 20%, 0.2. And you just plug in your values here in this equation, and in here, and then you get the minimum required, S top and S bottom. And we have here the minimum required. So let's say if this here says 1,000, this also says 1,000, it means that any beam with S top and bottom more than 1,000 should be good for you. You can use it. And then based on the beam size, we can figure out the amount of pre-stressing. It doesn't mean that this is going to be the most economic beam, but it means this is going to be the smallest beam in size that you can apply. Because you can go to a very small beam, but you need lots of strengths, right? To make it work, to make it support your dead load and life load and superimposed dead load. So it may not be the best beam that you need to pick for your case. But it means it's going to be the smallest beam in section that you can pick for your beam based on this loading and the span and the material properties that you pick. Now, when you pick a beam, you're not going to go with exactly 1,000, let's say, inch cubed for the S top and S bottom. You need to go slightly larger because in many cases, you cannot really fit all of the strands in the beam that you pick. You can go to a very small beam. It's going to satisfy all the stress conditions, stresses at the time of transfer and at the service level. Top and bottom, they're going to be okay. But the number of strands is going to be a lot. You don't want to go with this because the cost is going to be big. So in a case like this, you're going to go with larger S top and S bottom, and then you can control the number of strands that you like to put there. This is the reason in the PCI book, you're going to see lots of values and pre-solved examples for you, or pre-solved beams and double T's and things like that. This say, for example, yeah, go ahead, question.
So I had a question about the ST and SB.
Yeah.
In one of the slides from like earlier in the semester, like it says ST equals Y over 1 over Y.
Which slide set?
It's in like the one of the first ones, like the let me see.
I think you mean I instead of one.
The design review, the reinforced concrete design review. It says S or ST equals 1 over YT, and SB equals 1 over YB.
Here?
Yeah.
Yeah. This is I and this is I.
Oh, okay. I read it wrong.
That's fine. Yeah, you thought this is one, Yeah, it looks like one. It looks like.
Sorry.
This one. No worries. So what I'm trying to say here, that you have this tool, and instead of just throwing a beam size here, there is a way of coming up with the minimum required section properties. It doesn't mean that you're going to be going really to this minimum required section properties. Otherwise, you may have lots of cables and strains. But with this tool here, with this couple of values, you ensure that you don't really need to go through the hassle by picking a beam, and then after that, the beam is not good because you are going beyond the limits for the stressors. This simple two equations, you can come up with section properties that if you go to a larger size or with another section that has higher ST than required and higher SB than required, you're in good shape. Your stress is not going to be a problem. And you ensure here that you can satisfy it. And this is exactly what happened in our example. Based on this example, we said that the minimum section property, section modulus, top is going to be this value. Minimum, bottom is going to be this value, right? So we picked these two values. And then we said, let's look here, let's open the table and look for something good for us. We decided here to go with this section. And we found out that as top is going to be in good shape, I mean close. When you say here 36 versus 48, you say you have good room. But when we come to the top, it just happened that we have plenty of section modulus here. And look at the section here because you have this big flange. The good thing about this big flange is going to serve here so that you can drive or walk or use it, right? This is going to be like the final deck that you're going to be using. This is the reason that S top here is really high compared to S bottom. I mean, it makes sense, right? But you said this is going to be good. Cost is going to be okay. 48 inch should be fine. And to bring the stresses to the limit, this is going to be my minimum values. If I'm going to go here to this limit, it means I should be fine. I mean, I'm okay. The stress-wise, I should be fine. So now I kind of confirmed that the stress is going to be in good shape. The other factor is going to be number of strains. How many strains I need to put there? Because I can bring you another section, shallower section, let's say 36 inch or 24 inch, and then it's going to be satisfying these two requirements, S top and S bottom. But the bad thing is going to be number of strains. You're not going to like it. You're going to say, this is not good. Let me just move to this section because this section is going to give me control number of strains, like 12, for example. If you're going to go with the other one, I need 20. Now you go to the market and say, guys, can you give me like 36 inch and 20 strains? They're going to say, we don't have it. No one's going to be asking for something like this. Then you say, okay, let me go to a deeper section, bigger section, and reduce number of strains. So this is like one step in the design. And instead of having all the stresses calculated out for you, you're going to have something to take you to the section you need. This here reminds me again with the concept that I went with at the beginning. I said we have two ways of design when you have conventional concrete beam. One method, you throw the rebars, which means that you, now if I like to take it here to this pre-stressed thing, I'm going to say, you pick any section you want. And then you put in your equations. And then you check the stresses top and bottom. And then you say, wow, I have plenty of room. Can I reduce the size? You're going to say, okay, let me change the size. You're going to be trying many sections before you come close to the one that's going to take the stresses beyond the limit, beyond the allowable limit. You're going to say, this is not good. I need to stop here. Okay, so this is the first method. Second method of conventional concrete, you're going to be setting up phi min is going to be equal to m sub u, and this is going to be numerical value. Based on this, you solve for AS. Now you need to know how much AS is needed in square inches. Now I have it. Now I'm going to say I'm going to be using number 7. Number 7 rebar has 0.6 square inches for cross-section area. Let me figure out number of rebars. Let me now try phi min and be sure that it goes above m sub u. This is going to be now the second method. Now in pre-stress, very similar to this concept, I'm going to say, let me solve here for the minimum S bottom and S top required. Go to the table, pick the beam section, like in this case, that was a single T, the 1048, right? And if this section would give me higher S top and bottom than the minimum required, I should be fine. But you know what? Let me also check the stresses back again. So I know I don't really have plenty of room because the section I picked was right there, right above the limit. And if I need to go to a larger, just because I'd like to reduce number of strands. Make sense? Questions?
What's the table? Because I'm looking at the PCI handbook right now. What table or what page would I find the table of the different ones to
The
pick?
table is not really for the PCI. There's more than one table for it, but I can share this with you if you like. And you can look it up. You can just look it up online. You say ST or 10 ST48, and you can download something like this. It depends, of course, on what version. Because this problem that I have it here in this slide set is going to be based on the textbook. So I have to carry all the numbers just in case if you like to look at it. But look at this. They give you here all the section properties. It could be a little bit different from the one that we have in our problem, right? And then it says here it's going to be number of strands. Look at this, 20 strands, and the diameter of the strand in terms of 16th. So this is going to be 8. 8 means what? Half inch strands. This is the one we use, right? So this one here, it says if you put here 14 strands, half inch. See this? 14.8. 148 means 14 strands, half inch. How about this one here? What does it mean? 24 strands, half inch. 18 strands, half inch. I said, okay. And then it give you here the span, and then give you here the total safe superimposed service load and camber. For each span, you can have the load. Same thing. For each span, you can have the load. This is kind of an older book, actually. This copy from an older book. But give me a second here. Let me look for a recent one.
Thank you.
No problem. Here's double T's. Okay.
Awesome. Thank you.
Here's the double T's. And just, you know, because I had this question and then, okay. This here Y, which is the same as E. At the end, at the center. Okay. So in some cases, we have this EC. In some cases, we have EE. You guys see this before, right? And then you ask, what does it mean by EE? Does E stands for the, like the effective? And E stands for the end. So it's going to be eccentricity at end of the beam. And this one here is going to be eccentricity at center. What does it mean by that? Let me open the slide set real quick. There's something here that I want to show you before. Excuse me. The eccentricity here at the end, the eccentricity here at the end is going to be equal to 0 because it goes to the center. So usually we try to set the eccentricity at the end is going to be equal to 0. But this is not the case here. Look at this. Eccentricity is not equal to 0 at the end. But we try to simplify it and just set the stress at the end of the beam again to be equal to 0. Just trying here to look for some examples for beams that shows eccentricity at the end, eccentricity at the center. I don't see it here. I hope that anyways. So again, EE and EC, this gonna be the two values, right? But usually they're gonna be the same. So EE and EC is gonna be the eccentricity at the end, which means this YS end and YS center. Now this gonna be the way that you call it. They don't call it E anymore. So anyway. So if you look here for the smaller sections, right, you're going to see the strands are just straight. But to gain higher strengths, they're going to drape it. So at the center, at the end, is going to be a 12-inch. At the center is going to be a 3.5-inch from the bottom. If this makes sense to you. And again, this is going to be like number of strands, 12, and here is going to be the diameter. So here you have 6, half-inch, 14, half-inch. And look at this. If you have it straight, it's going to be S. So this here is straight, and this makes sense. When you have it straight, eccentricity at the center is going to be the same eccentricity at the end. When you have it draped, you're going to have this. How many are draped? It's going to be 1. You see this? D and then 1. Number of depression points. It's going to be 1 depression point. 1 point in the middle is going to be coming down. So the strand is going to look like this. Let's say here's the beam. The strand is going to be coming like this. Here's the beginning of the beam. It's not 2 points. 2 points, if this is equals to 2, you're going to see it coming this way. Something like that. 1 versus 2. D1 is giving only 1 point. Usually in double T's is giving only 1 point. You don't really need 2 points. All
Do
right.
we need this sheet for the exam, Professor?
This one?
Yeah.
You can use it if you want to, but you don't really need to. If I have a section that I want you to analyze, I'm just going to give you this section of it. So I'm going to take a snapshot of this and just give it to you. It's going to have all the properties, right? So you don't have to look it up. It's giving your hand on the problem itself in the exam. Okay.
Thank you.
So the single T is not common anymore. And as you see here, the piece of paper that I showed you, or the page, the PDF, is kind of old. Now, all what you have is going to be double T. Single T is going to be hard to stabilize it. If you think about it, you say, why would I use this? What's going to be the benefit of this? Why don't I just have a couple of whips? It's going to be like this. So at least I can just put it in any floor. In the yard, right? I can just put it this way. It's going to be self-stable. But this one, how would you do it? I mean, just imagine, how would you carry it? I mean, how would you put it on the floor? You need to have a support to it, right? This one, you don't really need any support. You can just sit it on the floor like this. This is why no one is using this ST. I mean, I never used it. This is what we use. Double T is what we use. And 24 inch is very common. 28 inch is not common. The 24 inch is the one that we really use. This one here. And we can go with 8 feet or we can go with 10 feet. Depends on the precursor, what's available. But usually it's very common that you use here 24 inch deep for the depth. Not including the top concrete. So you have here some concrete topping that we add. And this usually is going to be 3 inches. It shows here 2 inches, but usually in California here we go 3 inches for the diaphragm, for the sizing. Any questions before we go?
Yeah, how long are we gonna have for the exam?
3 hours? Is this good? You need more? 2 hours is good?
8 hours.
8 hours? No. This says here 8 feet. Where's the 8 hours? Where did you take it from? Okay. Yeah, it should be 2 to 3 hours. 2 to 3 hours. Next time we'll talk about this in detail.
Thank you.
No problem. All right. You guys have a good night.
Professor,
Yes, go ahead, please. Yeah.
you say for the for the exam you will not let us use the Excel sheet.
You cannot use the Excel sheet. You can
Okay.
you can have your notes, but you cannot use the Excel sheet.
That mean we have, because you mentioned before that the question will be take a long time to solve, like some kind of a questions, like the formulas and.
Not really long time, because if I give you a section like this, right? You're
Yeah,
getting
you
all
will
the
give us
properties.
like all the stuff we just plug in and.
Yeah, so it's gonna be simple for you.
Okay.
Because let me tell you why I don't want you to use a spreadsheet, because we can all get together, we can do a very fancy, nice spreadsheet, and everybody can just do it in a couple of minutes, and we don't know exactly how it works, right? We don't want this to happen. So where's the exam about? What's the exam is gonna be about then? Don't you agree?
Yes.
Okay, all right.
So, Professor, also I have another question. Do you give us review example, like exam review exam problem?
Yes, we're gonna review. We're gonna review. Before the exam, we're gonna go through a review. I'm gonna show you exactly how the exam is gonna look like, so you're not surprised.
Okay, good. Thank you.
All
And it's what more? Oh, so the exam will be through the Zoom or
Proctoria, you mean Proctoria? Yes.
or
I'm
Proctorio?
gonna be, yeah, it's gonna be Proctoria. I'm gonna be on my Zoom. So if you have any questions, you can ask me.
Okay.
I'm not gonna let you go and just go and do my business. No, I'm gonna be there. If you have any question, just come by and join the meeting and ask me my question. It's
Okay.
I'm gonna be logging to your class, meeting, not to the office hours, giving the class.
Okay, good. We will talk more in the next week, right, about the exam and everything.
Yes, absolutely.
Okay. Good. Thank you, Professor. Have a good night.
Good night.
Hey, Professor, I was like 10 minutes late and I think you marked me absent.
Oscar, right?
Yes.
I guess I put you on. Hold on. Let me check. I remember, Oscar, when you came by, I put you on, but give me a second.